Hello and welcome to today's webinar, Tips to Find the Right Optics for Your Image Sensor. Sorry about that, small technical difficulty. Brought to you by Vision Systems Design and Teledyne E2V. My name is Chris McClune. I'm the Editor-in-Chief of Vision Systems Design, and I'll be your moderator today. Our speakers today are Marie-Charlotte Leclerc, Product Marketing Manager, Teledyne E2V, and Pierre Fereyre, Senior Principal Engineer at Teledyne E2V. This webinar is both live and interactive, and a huge part of these webinars is our discussion with you. So please ask questions at any time via the Ask a Question box in the presentation window. We will answer as many of these questions as we can during the Q&A after our presentation. If you have any technical difficulties during the webinar, just type your issue into the Ask a Question box, and a member of our team will assist you. A copy of today's presentation can be found in the Event Resources area located under the Ask a Question box. If you are running pop-up blocking software, you will need to disable it to view the webinar, and in addition, we recommend that you close down all other applications for better performance. For your convenience, this presentation will be available for on-demand viewing within 24 hours of this live event, and a reminder email will be sent to all registrants containing a link to the presentation for on-demand viewing. It will also be accessible from the Vision Systems Design homepage at www.vision-systems.com. So with all that said, Marie-Charlotte and Pierre, let's get started.
Okay. Thank you, Chris. Hi, everyone. We are about to spend some 40 minutes together. And before even starting our presentation, we would like just to present you briefly who's talking to you today, so who we are and what we do. So as Chris introduced, Pierre and I are both working for Teledyne E2V, which is a world-leading provider of high-performance CMOS image sensors and subsystems. We provide, our company provides differentiated solutions for professional imaging applications as standard or fully customized solution. This is the kind of the DNA of our company, not providing commodity solution, but dedicated imaging solution that brings you value. So we truly provide a dedicated solution. The point is to give you the little plus or big plus that can make a difference for you and for your customers. Just to mention as well that we are not new to the field of imaging. We have provided such solution for decades now, with over 200 customers worldwide and billions of units shipped every year. We also to mention that we are part of the Teledyne group, which is an aggregate of dozens of independent technology companies, with one of its main focuses in imaging. So all of that to say that we do know about image sensors, which is good because it's one of the topics of today. So if you are attending this webinar, I guess that you have in your job to develop or support vision systems or systems that are using vision, and they all rely at some point on image sensors. But the performance and the image quality of your vision system does not come from the image sensor. It does not come from the lens. It comes really from the combination of the image sensor and the lens. And I think we can all agree that this task of selecting optics for an image sensor for both of them to work together is quite complex and can be critical. So I took here the example, three different examples, three different situations that you can see here. And in these three situations, in fact, something went wrong. Something, in fact, that we can directly link to the specificities of some image sensors that are not being considered. So on the left situation, you see a landscape with shadows in the corners. So if the images coming out of your system are meant to be analyzed by humans, it could give a bad impression on the quality of your system. If those images are meant to be analyzed by a computing system, it may affect the result of the computation in the corners and undermine the effective field of view of your system. So that's the first situation we have on the left. In the middle picture, situation 2, you can see that part of the image is blurred. So a typical PCB inspection system will not be able to analyze, inspect all the components on this image. And finally, on the third image on the right, you can see that the image is pretty dark. So imagine that you have a traffic or security camera, then you won't be able to see much in this scenario. So these three situations, in fact, they can be linked to a wrong decision in the optics plus image sensor combination. And our objective today is that by the end of the webinar, you will be able to get what went wrong in these situations by understanding some specificities of the image sensors. So let's go now into the presentation. So what we suggest today for the presentation is to start from a simple observation about the image sensors, which is that the pixels of image sensors are getting smaller and smaller. From that observation, I will let my colleague Pierre take over to explain you the concrete implications it can have on the optical performance of a system and on the choice you can have in terms of optics, the challenge it can raise. And finally, we are not only here to talk about problems, so we'll provide you some solutions. We'll present you several solutions that can be used to ensure a proper and efficient combination of your image sensors and optics. So let's start with a simple observation we can all agree on, I think, is that the pixels of image sensors are getting smaller and smaller. Because if there is one big trend of the image sensor industry we can draw, it's the permanent race we see towards ever smaller pixels. To illustrate it, let's have a look at this timeline you see on the top of the slide. So it represents the evolution of global shutter pixel size from main CMOS manufacturers over the past 10 years. You can see some blue points, which corresponds to Teledyne E2V products. So the pixel sizes and pixel use in Teledyne E2V products with the name of the family below. For the gray points, it corresponds to pixel sizes used by other image sensor manufacturers. So one can easily notice that there is a general trend across the whole industry to reduce the pixel size. And you can notice that over 5 years only for the most advanced image sensors, the pixel pitch has been divided by 2 almost. So smaller pixel, what does it mean? It means smaller die for equivalent resolution and on-chip functions. Smaller dies also mean, in fact, access to more compact and more advanced packaging technologies, which enables to drastically reduce the size of the image sensor as well. So you can see below the chart being displayed a timeline. So I took here the example of 3 different image sensors we released, all of them having a full HD resolution, so 2 megapixel. You can see on the left the Sapphire sensor that we released in 2016, which rely on a 4.5 micron pixel and CLGA package. 2 years ago, the Emerald 2M coming, same resolution, but this time 0.8 micron pixel and fan-out package. You can see the evolution of the size. And finally, last year with the release of Topaz 2M, our latest megapixel sensor, which rely on a 2.5 micron pixel pitch and pip scale package technology. So you can see the progressive shift, shrink in image sensor side so that the pixel size decrease. It enables also to benefit from the advances in packaging, so that you see that over 5 years only, the footprint, the size of the image sensor itself has been divided by 4. So it's 4 times smaller now. So why do image sensor manufacturers like us enter in a race towards ever smaller pixels? It's not for the technological challenge, for sure. A first answer lies, in fact, in the fact that if you have smaller pixels, then you have smaller dies, which means you can put more dies on your wafer, and so it can reduce both the size and the cost of the image sensor. That's the first explanation, but in fact, it's not the only one. The second explanation is in fact directly linked to the optics and the impact it has on the size and the cost of a typical vision system. More precisely, I'm talking about the image size related. So you have here represented on the left image circle with the image size inside. The image circle, just to remind, is the cross section of the of the cone of light that is transmitted by the optics. This image circle, it leads you to an image size, as you can see here, in inches. And it is in fact a legacy we have from the old tube cameras. So due to some manufacturing limitation, in fact, only 2/3 of the mechanical surface of the tube was effectively used and active. So today we have the equivalent of 1 inch, which corresponds to 2/3 of that, so 16 millimeters approximately. So you can see the image circle and can have an image size can have a significant impact on the side of your image system. I display here some of the most common optical image sizes that are used in the industrial vision applications. So you can see that if I went from an APS-C type of lens to C-mount type of lens, I can significantly reduce the size and in fact the cost of my system. And same if I had to switch from a C-mount going down to an S-mount for equivalent parameter. So assume that I want to go from APS-C to C-mount, or from C-mount to S-mount now by keeping the same resolution to get at the end something cheaper and something smaller. What does it mean in terms of image sensor? Of course, it means having smaller pixels. In the table on the right of this slide, I computed, as you can see, the maximum pixel pitch that you can allow to fit a certain resolution into one specific optical format. So you see in the table, you have on the left the resolution and the corresponding pixel array, quite precise. And then you have the maximum pixel pitch for APS-C. Then you have some numbers for C-mount pico lenses and S-mount on the right. So what you can see is to fit with smaller lenses and smaller mounts associated, we have to decrease the pixel size, and in fact, we have to decrease it quite a lot. For instance, assume that I have a 2 megapixel solution, so full HD, that I want to reduce from a 1 inch format to a 2/3 of inch format. You can see here easily from the table that we have to quite drastically reduce the maximum pixel pitch we can allow, going to something in the range of 7 micron maximum to 4.84 micron. So that reduces quite a lot the maximum pixel pitch you can allow. And as soon as you get to higher resolution and more constrained lens mount, if I take now the example of a higher resolution solution, so 8K by 8K square, 60-ish megapixel, you can see that if I want this solution to fit with APS-C mount lenses, I cannot afford to have a pixel pitch larger than 2.5 micron, for instance. So you see that going to a smaller optical format, it has a direct consequence on the pixel pitch, the maximum pixel size you can allow, and the change is quite drastic if you were to reduce to a smaller optical format. So in fact, to address the need to keep reducing vision systems size and costs, both on the side of the image sensor, but also on the side of the optics, image sensor manufacturers have no choice but shrink the pixel size and quite drastically, as you see. So this is a general trend, as we have seen, and in fact, it has direct consequence and implication on the optical performance you can expect from the image sensor, and also on the choice of optics you can make for your image sensor. So this is what my colleague Pierre will now explain you.
So thanks, Marie-Charlotte. I propose in this part to explore the application and design of the CMOS pixel and consideration oriented towards optical performance in general. So first slide is a reminder of a previous session we had, because it's more or less linked. So we expose the two essential parameters to guarantee a good image quality, which are the signal to noise ratio and the spatial resolution. So also these are general consideration. They require even more attention when designing an image sensor made of very small pixels. So the performance is pushed to the limits to the technology generally, and no effects is to be neglected. So the pixel steps becoming close to the wavelengths, to the pixel pitch, I mean. Some effects becomes important, such as the diffraction or perimeter effects, optical or electronic crosstalk, and so on. So the arrangement in the large pixel arrays increase the difficulty to make these characteristics uniform throughout the whole image. So the implication on optical performance, you see the shape and the angle of the light cone reaching the surface of the macrolens is related to the characteristics of the main lens used of the imaging application. So I mean aperture and focal length and so on. So also the thickness of the stack of oxide you have on top of the pixel on metals that are shown in blue in the CMOS technology plays a role in light collection. So in the figure in the middle, the fill factor equals the lowercase xy divided by the uppercase xy, and that depicts the ratio of sensitive area of the CMOS pixel, it's named fill factor. So an alternative solution is to design a first-order microlens structure for each pixel that is called a microlens to avoid the constraints related to the operational condition. So microlens arrays, because we are talking about arrays of pixels, are fabricated using reflow techniques on photoresist, on resin layers to achieve a high numerical aperture ranging typically for 0.2 to 0.5 with pixel pitch of a few microns. So the most efficient manufacturing process allows to join the lens together, and it's called gapless microlens array. In this condition, the pixel QE almost equals the photodiode's QE that is depicted on the right. So a difficulty arises when the light rays from the border parts of the pixel are focused on opaque parts of the pixel, such as metals. This may lead to a loss of optical efficiency, of course, and the macrolens shape must be optimized for each application with a real optical design that work at the semiconductor frontier. So the smaller the pixel, the more the design constraint increase because the fill factor decrease. Also, the aspect ratio, which is the optical stacked 8 divided by the pitch of the pixel, also increases. So it may be necessary to compensate for some optical effects by adjusting the entire array of microlenses and locally. So let's talk about this angular response and the numerical aperture of the pixel. So the pixel and its microlens can be understood as a small first-order optical system, including a focal lens having a field of view, a pupil, and thus a numerical aperture. So the numerical aperture is the range of angles over which the pixel can accept light. So all of these parameters are defined by the physical layers present above the photodiode. So for example, the conductive metals lines or the transparent separating layers. Understanding that the metals can also reflect light or diffract light. So the numerical aperture is characterized by the angular response of or attenuation of the signal according to the main angle of the incident light rays, as it is depicted on the right figure. This demonstrates that the angular limit from the purely geometrical consideration is not a strict limit for the rays. But when combined with the main lens, the microlens become a kind of additional element in the optical chain. So if the aperture of the main lens is larger, means a small f number, then the aperture of the pixel, the gain in exposure will not be very effective because the pixel will limit. So a pixel with a small numerical aperture will not allow to work with very open lenses. That's a consequence, direct consequence. And this is illustrated on the graph on the right, where you will cross some angles in the angular response that give you less than 100% response. So this can penalize the implementation in the application, either because the natural light is insufficient, or because the artificial light resources will become a physical or a cost limit. So, so if we consider the main optic, it produces a diffraction pattern that is well known. This pattern is projected on the sensor plane. And the spatial resolution of this pattern is called Airy disk, is non-uniform as described on the figure on the left. So the diameter of the circle is proportional to the wavelength and the f number. As the Airy disk grows, it eventually covers also adjacent pixels, producing blur in the conditions of the scheme above, on the figure above. Just before the size of the Airy disk exceeds the size of the pixel, the lens will be at its best sharpness, depending only on the pixels. So in other words, the pixel size determines when diffraction becomes visible in the condition of the scheme that is shown below. So as a result, small pixels will be oversized by the Airy disk much sooner. So the figure on the right shows the minimum pixel pitch versus the f number for different wavelengths based on Rayleigh criterion, where the pixel match the diameter of the Airy disk. For example, depending on the wavelength, a pixel of 2.5 micron will best perform in the minimum aperture range of f over 2.5 to f over 5.6. So let's look at the focal plane. So we identify a circle named circle of confusion that defines the smallest point that is distinguishable in the image. So we generally consider a circle that the diameter is equal or fits the pixel pitch. So as shown on the figure on the left, on the figures on the left, the circle of confusion match a short or long depth of focus, respectively to a wide open or closed aperture. So as illustrated on the figure on the right, the optical and the sensor alignment are subject to mechanical tolerance, especially when assembling the chip in the package or the sensor in the camera. Sometimes it can be both misalignment at the same time, which together lead to a focal plane parallelism defect. It is important that the depth of focus is within this range to ensure that the image is sharp at all points of the pixel array. So I propose you this figure to see where we are with those two effects. So unfortunately, when the aperture of the optics or the f number varies, the diffraction of the Airy spots and the divergence of rays varies in the opposite direction. So is it clear that the adjustment of the operating range is a trade-off between the two, as pictured in the diagram on the screen? So the figure shows three zones. The lower area of the graph in blue corresponds to a sharpness defect related to the defocus blur. The upper area in brown represents a blur related to the optical diffraction. And finally, the green area in the center is the working range. So it should be noted that this range is narrow, which strongly constrains the mechanical specification of the camera assembly. For example, a pixel of 2.5 micron will require a parallelism of maximum 15 micron for f over 2.8 aperture. So these figures are the result of a simulation of the blurring effect on a Nyquist and half Nyquist contraction target. So the target on the top right is the theory, where the target on the bottom right is the reality sampled by the pixel. So in this case, the blur is dominated by the diffraction effect that is shown by the modulation transfer, which is the graph in the middle. And the figure that is on bottom left. So this is an example of blur dominated by diffraction. Let's see what appears to be blur dominated by defocus. So with lower f number, the blur starts to dominate even in the final image. Is the same as at the end, in fact, thanks to respect of working range condition shown in the previous slide, that's the slide 14, inside the green area. So as a summary, for this part, we have explored two important leverages for image quality, such as sensitivity and spatial resolution. There is a third leverage, which is the exposure time, whose compromise will be the motion blur. So these three parameters constitute the exposure triangle, which enables to determine which trade-offs are possible in the application to obtain the best image quality. So now I propose to discuss some technology solutions to improve the performance of CMOS pixels. So we can explore now some possible ways to offer improvement with the technology. So first of all, a dedicated technology to improve light collection and angular response at once. So for a relatively long period of time, CMOS technology has very little specificity for imaging. Now, complex stacks with layers of optimized optical index have emerged, especially with the reduction of pixel size. So in front illumination, for example, or FSI, the light pipes on separating walls plays a role of light concentrator. This is the figure on the left. In backside illumination, that is the figure on the right, or BSI. Metal routing is no longer a constraint because it is in opposite side of the sensing. And pixel isolation is optimized with deep trench insulation, or named DTI. And therefore, the angle of response is optimal with BSI. So there are also design tricks. So as shown in the figure on the left, the light rays concentrated by the pixel at the center of the array form a solid angle or three-dimensional cone that is bounded by an angle to the normal plane called the marginal ray angle, or MRA. The central ray of the solid cone is called chief ray. If we consider a pixel located at the edge of the array, the cone is tilted, as depicted on the figure on the left. And the value of the chief ray angle is the value of the shift is the chief ray angle, or CRA. So on the right, figure A, we note that the macro lens perform well, concentrating the rays without loss when we are normal angle in the center of the array. When the rays are oblique, figure B, a large part of the rays are masked by the metals, which produces vignetting effect. So to correct this, we project the C array on the sensor focal plane to determine the delta X that is noted on the right figure. That is the value of shift necessary to concentrate the ray at the center of the photodiode. So obviously this correction requires a perfect match of the main optics and the sensor and the design of the sensor. So this is a good transition for the next part of the presentation. I will leave it to Marie-Charlotte, who will show the solution matching the optics and the image sensor.
Yeah. So yes, as Pierre just explained, there are solutions that can be found at image sensor level to improve some optical parameters or to enable a wider flexibility in terms of choice of optics. Yet the image sensor itself cannot do everything and cannot solve all the challenges. So this is what I wanted to show you on this slide. If you look at the graph on the right, which shows you the evolution of the depth of field with the working distance for a constant field of view in two different situations. So for the dark blue part, you can see the corresponding depth of field in case of a 5 micron pixel pitch. For the light blue section on the graph, you can see what we would get for a pixel pitch 2 times smaller, so 2.5 micron. So you have here two typical scenarios: a small pixel pitch and what is a medium or previous legacy technology of pixel pitch that we see in the industry today. What you can see on the graph. First of all, regarding the pixel pitch, the pixel size, we can all agree it's a parameter you can choose. You can choose the sensor you want. You can choose the pixel pitch you want. So that is something you control and you can choose when you develop your vision system. What you cannot choose and what we likely not control is the conditions in which your vision systems or systems using vision will be used by your customers likely. So this is defined, fixed, and it's defined by the overall setup of your customer or by its use cases. So if we go from what is defined, so the working distance, which is linked to the use case of your customer or your typical use case, you see on the graph on the left, when working at a distance of 1 meter, typically, you have a lot of flexibility and plenty of options. The range of your depth of field is quite large, no matter if you use a 5 micron or the 2.5 micron. And as you want to work at longer distances, it improves. But in the opposite way, as soon as you want to have a closer distance between your vision system and the object or the person you want to observe, then you see that it's getting a bit tricky. Many industrial applications, in fact, have a typical working distance in the range of a few dozen of centimeters, so typically between 30 and 60 centimeters, I would say, for instance. So assume, for use case, you want to look at a QR code or barcode that is on a parcel that is itself moving on a conveyor belt. You see the camera on the top. So assuming the top of the parcel is at 55 centimeters from this camera, then you can see on the graph on the right the corresponding depth of field for that specific working distance. Now imagine that now you have a bigger parcel, so that the top of your parcel, new parcel, is located not at 55 anymore, but at 30 centimeters from your camera. Then your working distance reduced to 30 centimeters. And you can see that the depth of field is getting even tighter and tighter. So that is represented in the pink or red dot line you can see on the right graph. So the scenario is not the same anymore, and the depth of field is getting even more narrow. Could be fine if you're looking at the flat surface, QR code, but as long as you want to work at different working distances and that are close, or that you have some bulk object, can be for the mechanical part, if you want to have a full view at distance that can vary and that are still close to your camera or your system, then you may not be able to get sufficient depth of field to see a full, clear image. This is purely optical observation. And so it implies that in some use case, for some application, in some scenario, you will need a solution not only with the image sensor, but with the combination of the sensor and the lens to enable a broader working distance. The solutions to that problem exist today. We said we wanted to provide some solution, ideas of solution. Solution exists today under the form of multi-focus or autofocus modules, type of term, which includes both the image sensor and the lens. So we are in this typical case of lens plus image sensor combination, and they enable to benefit from extended depth of field, as I want to illustrate here. So you can see on an example on the left, you can see the original image that I took with the full field of view. You see on this image 3 different objects that we would like to observe. So the first one on the left, you have a target that is located at 10 centimeters from my module. Then in the middle, you have a calendar located at 1.5 meters of the module. And finally, on the right, at 30 centimeters of my module, I have a barcode. And so as we noticed from the graph on the previous slide, we cannot have everything in focus with that typical scenario, knowing that, as mentioned on the bottom, in this typical case, for instance, pixel pitch I took 2.5 micron, which enables my solution, for instance, to fit with M12 mount, so cost-effective and compact lenses. And I took an f/4 aperture, which is quite open. At least can be more open than what we use typically for decoding barcode usually. So quite larger aperture to be able to still get light sensitivity. So I don't have everything in focus on the left with just this focus. But you can see on the right the cropped images that are enabled by the focus adjustment implemented inside this multi/autofocus module. So you see on the left, it's a fully clear image of the target located at 10 centimeters. I can also get a clear image of the calendar located above 1 meter from the module, and from our barcode at the 10 centimeter. At 10 centimeter, I have a clear image as well. So if you remember the dilemma that was expressed by Pierre a few minutes ago, there is a compromise to make between having a wide lens aperture, so light sensitivity, lot of light coming, and depth of focus, which defines would define a bit the flexibility I have in terms of working distance and setup. So with this multi or autofocus module solution, you see that we can bypass this issue by having a wider aperture optics, in this example f/4, and still benefit from an extended depth of field going from 10 centimeters to the infinite, and that with a small pixel pitch, the most advanced existing today, 2.5 micron. So now that I showed you the benefits of those kind of solution, what it can provide in terms of optical, from an optical point of view, I just want to give you some more insight of what they look like. So talking about multi-autofocus modules, I'm talking about this typical solution. What is nice as well with those type of solutions that are emerging, it's not only convenient from an optical point of view and solving some optical challenges, it's also convenient solution because it's turnkey and ready for integration. Why is it turnkey? It includes, in fact, so you have a dedicated image sensor board. So you have your image sensor on a dedicated board. You have the front face, as you can see, the lens holder, and even you can benefit from optional lens in our case. Those type solutions can be quite convenient if you're working or planning to develop embedded vision solutions. So not relying on a PC anymore, but on a single board computer. In that case, you can benefit from the MIP interface. So directly compatible in terms of interface, directly compatible in terms of hardware as well, because you have, as you can see, the typical FFP, FTC connector. And in terms of control, you have the I2C that you can find on any embedded processing platform today for controlling the sensor and also the multi or autofocus, if you have this feature. This type of solution are also convenient because they enable instant integration. You have on top of this solution a development kit. So we typically provide a development kit that include all the necessary hardware and software for enable direct connection. So you have the adaptable anything provided along with the Linux drivers for NVIDIA, to quote just the most famous names. So turnkey solution, quite convenient for embedded vision, instant integration into your system, and finally, the perfect match between the image sensor and the lens. In our case, we're talking about a proprietary sensor to combine with multiple lens options, as you can see below. The point of those 3 different lens options is to enable you to have the solution that fits your needs. So you may want to benefit from the extended depth of field, and you may be in the typical critical challenging situation that we mentioned during this webinar. In which case, the multi-focus lens can be interesting because you can capture sharp images at various working distances. So you get sharp images, fast solution. We have also a fixed focus lens option. So if you want to have a lens, you don't need that broad working distance or to work at different distances, but still very close. You can have the lens included, which can save you the time and effort to select the lens. And we have seen that it can be challenging to assemble it, and making sure it's in focus and well in place. That can be quite challenging as well. So there is an option where you can have the lens included. And finally, if you want to keep the flexibility to change the lens at any time or to put the lens to your choice, your custom lens or whatever, the module can be provided without a lens. So those typical solutions, as the product we are showing here, which is the Optimum QM we just released, is quite a convenient solution from an integration point of view. And it's also a way to solve some of the dilemma and challenges that are coming with the reduction of pixel pitch and the new image technique. So to conclude, some key takeaways, because we are speaking for about 40 minutes now. If there is something to remind of the presentation, so in terms of context, as we have seen, to reduce the size and the bill of material of vision systems, image sensor manufacturers like us are entering in a permanent race to reduce the pixel size. Smaller pixels mean lower light sensitivity. It also means closer pixel aperture, as Pierre explained. And if you want to still get light, a direct consequence would be that you'd like to get wider aperture optics, but we've seen that it's at the expense of the depth of field. So a solution exists at sensor level, as Pierre explained, to alleviate these consequences, optimize pixel optical stack, the backside illuminated architecture, or the shifted microlenses, which enable to optimize the CRA of the image sensor. And on top of that, going one level above, innovative multi-autofocus module solution, which include the image sensor and the optics, are excellent way to combine lens sensitivity and wide working distance in the challenging context of ever smaller pixels. It's also a way to ensure that there is the perfect match between the image sensor and the lens. So in terms of tips, you have to remind some tips, because we were therefore providing some tips as well. The first one is to remind that to match the optics CRA with the CRA of your image sensor to be able to benefit from the maximum field of view and not getting shadows in the corner, for instance. A second tip, consider the pixel angular response, pixel aperture. When you're thinking about your dilemma in terms of optics, usually we think about the lens between the aperture and the depth of field dilemma. but the image sensor has to be taken into account as well because the pixel has a certain angular response. A third tip, you can have a look at the multi-autofocus solution existing if you need higher flexibility for your optical setup. And finally, keep in mind that a turnkey solution exists as optical module with optimized and combined image sensors and optics. So that is here for the end of the presentation. But just before switching to the Q&A session, I just wanted to let you know, if you enjoyed this webinar and you are curious to hear more about Teledyne E2V, you can have a look at the latest articles we released here. You have the QR code on the right if you want to flash, and this will be in the slides that you will be able to download after the presentation. So 2 of the latest articles we released about 3D imaging, for instance, or embedded vision, if that's of interest to you. Also to let you know that on November 29th, so in around 1 month, we'll be part of a panel discussion about the future of image sensors. And in any case, if you want to stay tuned on our content and what we can provide, you can subscribe to the newsletter by flashing this QR code at the bottom of the. So we thank you very much for your attention, and I think we can now switch to questions. Great.
Absolutely. Thank you both very much. We do have a number of questions, and we will try to get to as many as possible during the remaining time here. First, for Pierre, can we change the CRA of an image sensor to adapt to one of an optics?
Well, I would say yes, definitely yes. This is the way we are doing. We consider chief angle of the lenses to design the micro lens shift. Definitely yes. This is something we master during the image sensor design. This is something we can adapt for sure.
Okay, perfect. For Marie-Charlotte, you presented a multi-focus module solution. Is it available for sales, and how can I test it?
Yes, so the solution is available. So the product is named Optimum 2M. Going on the website, flashing the code, you can access the documentation. So Optimum 2M, a product we released, you can look at it on the internet. It's available for sale for the 3 options I mentioned, so no lens, fixed focus, or multi-focus. And you can evaluate it and test it. Yes, 2 options for this kind of modules. Either you want to test it on your computer because it's more convenient for you to work on the laptop. You have some codes. It's more convenient. In this case, we have what we call evaluation kit. It's a test camera to be plugged on the PC using the USB. That's the first solution, and we provide the evaluation software. Another solution, if you are more towards embedded vision, so not working with a PC, but with a single board computer, NVIDIA and XP-like, we have the modules along with the development kit that I was mentioning. So you have all the hardware and software provided, and we can help you as well to test that on the NVIDIA and XP or whatever. So 2 types of solutions available if you want.
Okay. Do the Optimum 2M have a tunable lens, and what are your thoughts? And I'll throw that out to both of you. What are your thoughts about tunable lenses in the future?
So does it have a tunable lens? Yes, yes, it has. It's a tunable lens. It's not mechanical principle, which makes the solution fast. In fact, it's more about changing the curvature of the light beam, which is quite convenient in that case. So this is what we have in the case of the multi-focus module option, tunable lens, and about the future. I would say that it's a bright future for the tunable lens. So as we have just shown, in some typical situation, if we are getting close, it's quite complicated to work at different working distance. So it gives more flexibility, and also with this permanent race to pixel size decrease, it's getting even more important to have this flexibility that can offer tunable lens.
Yeah, you have some example on which tunable lens is just mandatory.
It's getting mandatory.
Yeah.
It's getting even more crucial with the trend we see to reduce the pixel size to enable a smaller and more cost-effective system. So a bright future.
Okay, could you give us an idea of which products from Teledyne use tunable lenses?
At the moment, so it's this module, so at Teledyne E2V, our DNA initially, so we are image sensor manufacturers, which is why we know about the image sensors, and we really wanted to give you tips, not from a lens manufacturer point of view, but from an image sensor manufacturer point of view. So image sensor makers, but having more challenges coming with the lens plus image sensor combination. We decided to go for this module. So this is the first product with this tunable lens option. Optimum when that can fit the module. But it's the modules really, not the image sensor we provide usually.
Okay, let's see here. How does the autofocus module interface with the imaging sensor or camera? Is it built into the lens?
Yes, it's a proprietary solution we have with the tunable lens inside. It's you can control it. So I was showing. I will not go back to the slide. You can look for it in the 20-ish something slide. At the back of the module, I was showing you we have this FFC FPC connector. Some pins are dedicated to the I2C control. Usually, it enables to control the image sensor itself. In case of the multifocus, you can control it to the I2C signal as well. So control I2C by using the connector at the bottom of the.
Okay, let's see here. Just a real quick question for you about where you're located and your contact info. I think the contact info is on the final slide there, the thank you slide. But where are you located?
We are both located in Grenoble, so in France.
France.
We have offices, yes, mainly in France, Spain, and in the UK. We have some sales. We have sales office and technical support located a bit everywhere to provide local support in the right language and in the right time zone. But for us, we are located in.
Okay, and here this one's going to be again a more product-specific type of question. How is it possible to get an autofocus response time in less than 1 millisecond on the 2M multifocus MIPI module?
I see that someone looked at the product brochure, so well documented. The response time, so as I was mentioning about the technology itself, it's not mechanical, so it's not a mechanical part, it's not motorized lens. It's really about changing the curvature of the light beam, which is why it can be so fast from a technology point of view. Now about the implementation of the module plus your processing system inside your whole system. It's the typical response time of the technology, the product. Now it has to be linked with the latency and the processing time, or you can get on your processing platform. On a PC can be fine, on some embedded processing platform, and NXP or whatever, depending on the product you select. You can have some more latency linked to the processing system itself. But the technology, yes, below 1 millisecond response time because it's not mechanical. In fact.
Okay, next we'll get a little bit more into just, I guess, more onto maybe the tips side of things. And this question comes in, when in the process should the optics be matched to the image sensor?
Yeah, it can be considered from the beginning, but as I said, the pixel design is a mix of semiconductor and optical things. We can consider from the beginning because we have seen that all inside the pixel impacts the final performance, especially when we do the small pixels. So if there is something very specific in application, we must take care, we must consider from the beginning. But in the same time, for example, we can also adapt existing product. For example, we can adapt the micro lens shift to a particular lens system. Obviously, it's when it comes with an existing lens system. If you consider using modules, that makes no sense because our modules are perfectly fitting a lens and image.
If we're talking about sensitivities, I agree with Pierre from the very beginning, so from the development start. What can be interesting in the documentation and testing the image sensor, you can get the information from the manufacturer about the image sensor itself. You can look on the paper for compatible lens. And with the question on the module, a bit earlier I was mentioning two types of solution we have. Development kit, more for embedded board, or evaluation kit. In both cases, we have the lens folder. So after the part of theoretical and documentation study, you can select a few lenses and test it directly on the evaluation kit or development kit of the module if you want to test in real life what it would get, the combination of your image from the beginning.
Okay, if you could, from your perspective, is there a most common mistake that integrators make when selecting the optics for their image sensor?
Is yours this one?
Yeah. So from image sensor manufacturer point of view, and some common mistake that we see, and in fact it's what we try to answer and explain in this webinar. So as Pierre presented, for instance, at the beginning, the pixel has its own aperture, I would say. If you remember the curve, you will be able to see in the PDF download, but there is this curve of angular response of the pixel. So one common mistake we see is people saying, I want more light sensitivity, so I will open my lens even more. But at some point, as you will see typically on the curve of the graph, at some point, it doesn't make sense anymore, in fact, to open more your lens, because you don't get much benefits of it, or even no benefits on the light sensitivity and the light you get, but you lose in depth of focus. So
the figure that I'm just showing now.
That is displaying. Yeah. You can see the angular response. So we have seen one of the common mistakes, which was I will open my lens to a point where it doesn't make sense. So people are just losing depth of focus for no benefit. So I would say that's.
Yeah, the main mistake is to have a mismatch between the characteristic of the image sensor and the lens itself. So matching the two is very important.
Choose one. CRA also, and this is why we wanted to mention the CRA of the image sensor to be fit with the CRA of the lens. So as Pierre mentioned, we can fine-tune the CRA of the image sensor, and we also have usually several options of CRA on the image sensor. So matching this CRA to avoid the shadows in the corner, and really considering the pixel aperture or angular response to be able to make the right balance of light sensitivity and
what would you? I mean, we just talked about some of the mistakes that could be made, but what do you think is the greatest challenge facing vision systems designers when they're trying to match the right optics with their image sensor?
Challenge. Well, sometimes it's finding a lens to fit with the image sensor. So for that, from an image sensor manufacturer point of view, we are used to provide some suggestions of lens. So our technical support can provide some suggestions if you don't know where to start. We have some lens selection guide from time to time. The lens manufacturers also, almost all of them have now tools to find appropriate lenses, even starting with the image sensor itself. So just finding a lens. And yes, one of the challenge can be with this pixel size decrease. So it's a challenge for the image sensor manufacturer. It's also a challenge for the lens makers to be able to have those lenses compatible and optimized for smaller pixel pitch. So sometimes it's finding a lens that can match with a small pixel pitch. It's getting even more common, but that it's a permanent race. It can be challenging sometimes if you have some tough criteria for your lens already.
Maybe I can add something very, very obvious, but in every design, it's a matter of trade-off, in fact. So the big challenge will be to trade off in the performances and with regards to the application. But it is something very, very common in designing system or whatever.
Okay, perfect. Well, thank you very, very much, both of you. With that, we've come to the end of our program today. And as I mentioned at the start of this event, the session will be archived for future access, which should take place in about 24 hours. All registrants will receive an email with a link directly to the archived webinar. And please feel free to pass this link around to your colleagues. You can also access the archive at www.vision-systems.com. Finally, I'd like to thank Marie, Charlotte, and Pierre for sharing their time and expertise with us in this presentation, tips to find the right optics for your image sensor, Teledyne E2V for making today's event possible, and of course, you for attending. We look forward to seeing you at our next webinar, and until then, have a good one, and we'll see you soon. Thanks again, both of you.
Thanks, Chris. Thanks, everyone.
Thank you, Chris.
Bye.